Okay, so now it's time for the final session of this TIDES workshop with the panel discussion on disorder input systems for quantum technologies. Is it an opportunity or deterrent? So, Benjamin.
Thank you. So let's start this session. I prepared a few slides. I think that this topic could be a full workshop in itself. There are so many things to discuss. So I just prepare something to start a discussion, and I will let the panelists follow up and discuss what they think about practical application. So just a reminder of what we have learned this morning with the discussion on superfluid density and the optical conductivity response of a superconductor, which is the thing that is important for quantum technology. You remember that the superconductors has a vanishing sigma-1, ideally exponentially vanishing sigma-1, and a sigma-2 that encodes the inductive response, which is proportional to the superfluid stiffness or inversely proportional to frequency and penetration depth square. And this penetration depth square depends on disorder, following the standard TS formula. And you may remember that if you put disorder in a superconductor, you start from a clean situation where the number, the density, superfluid density is equal to the number of electrons within a factor. And once you plug disorder, this quantity, superfluid density, drops. And this is given, for instance, by this evolution of the penetration depth, and you can change language and talk about kinetic inductance, so the inductance of your superfluid, and just add the penetration depth, and you see that you have a direct proportionality. And for thin films, you have the Pearl length that is lambda square over d, which take into account the finite thickness. So the main properties for application is this kinetic inductance, which rewritten in terms of thin film properties is proportional to the sheet resistance, and which is inversely proportional to the superfluid density. Okay, now let's try to get a little bit of sense about this quantity in terms of values. Here, what I show you is a huge scale of resistance, which goes very high, up to mega ohms. It's a little bit ambitious, but I'm going to show you what it gives. So this is typically what you can expect for an aluminum film. It can be actually a little bit lower in terms of resistance, give it the thickness you want. This is not a true transition, it's a PowerPoint line. And if you compute the inductance, you get something in the range of 0.01 to 1 picohenry per square. And what we have seen during this conference is that you can keep superconductivity to a very large disorder up to a point where the superconductivity is destroyed. This is the superconductor insulator transition. You have a variety of transitions and possible intermediate state, whatever. But you have materials where this resistance can shoot up very high. We have seen it in this indium oxide. We have seen it also in nylon nitride with a Christoph strength. It can reach nearly 17 kilo ohm per square. And this gives you, naturally, if you believe this semi-classical Matisse-Bardeen formula, this gives you a boost of kinetic inductance by the same order of magnitude. And now you can get values of the order of 0.1 to maximally 10, actually a little bit more, 17 nanohenry per square. So this is the point of application, is to take benefits of this inductance in possible circuits and application. This is examples of values so that we extracted in our work for indium oxide, but you have more or less the same for nitride if you approach the superconductor insulator transition, and you see that you can reach a huge number. So nanohenry perhaps doesn't give you much information, but it's very large. So if you want to talk about, for instance, impedance, if you make a microwave circuits and microwave resonator, you can very quickly reach regimes where the impedance of your resonator is above the quantum of resistance.
But do you expect it's still valid in this limit? is VCS
I
in
don't-
a bad disorderly, which
I
is
don't-
not described by VCS anymore.
Anton would say.
I will.
Certainly.
Oh,
But in any case, I mean, if you measure the response, I mean, in a sense, we don't care that formula from an experimental point of view, right? For application, you just get something which is like some impedance with some frequency dependence, right? If it looks like an inductance, then
And I mean, you can
it's that inductance.
Exactly,
Right?
but
I mean-
square resistance is not anymore the right scaling or something like
Yeah,
that.
no, that I agree. But if one, in the sense of application, that is the number is the layer scale, right? That you care about. Whether it follows that.
Higher values that
it's more like, I mean, of course, like if there's an experimentalist, you might be interested in actually like some design guidelines, and this formula like works by an order of magnitude. I mean, you can easily get something that is 10 times larger, 10 times smaller than this, depending on what how square you take, what delta you take, because we know from Benjamin work that delta is not itself a well-defined quantity in strong disorder, but I mean, it will be hard to miss by, let's say, 3 orders of magnitude. Would be hard. So the idea is that it just gives you a motivation of why to go to high disorders in the first place.
you want to hold below 1 kilo per square, it's more or less correct. If you start to go above, then there is all this localization SIT effect, which makes a very simple point. When you have a resistance, see, it goes to 6 Kelvin, but if I plot it up to 300 Kelvin, resistance continue to grow from 300 Kelvin. It's a semiconductor. So which resistance, what is drawn? Okay, so we don't know. Then there is the gap issue. The gap is not TCE. Close to SIT, it's the fun for this physics. But for application, what matters is more just the microwave response, signal one. So what is also interesting here is that this impedance matters also for circuit quantum electrodynamic schemes because the 0-point fluctuations of the voltages, if you do a resonator, scales like square root of z. And as I said, this number is huge actually when you are very disordered or you have a very low superfluid density. And then you can also engineer strong coupling to any charge dipoles in that situation. And that is interesting because you have tons of things that you can couple possibly in perhaps in a strong way to such kind of resonators. What's next? Yes, so application which are most popular one and the most known one is to actually replace or try to replace the linear inductance that is used in circuits, and this linear inductance is made of chains of adjacent junctions, and with that you can build a variety of circuits like the famous fluxonium. You can make inductively shunted transmon. You can make a variety of protected, also potentially protected qubits like this one, which I think has been partially realized with partially successful protection, whatever. And the deal is that this chain to attain very large inductance, so we are talking about now microhenry total, this chain is a little bit complicated. It's doable, technology exists, people can do that in lab, but imagine you need to make a 1 million qubit quantum processor, each of them with a chain of, I don't know how many junctions they put, 1,000 perhaps, or few hundreds.
Hundreds,
Few hundreds. Then scalability and errors in the fabrication becomes drastic, right? So it's super tempting, obviously, to replace the chain by just a line, which is just take your preferred disordered superconductors, you lift off, you edge, whatever, and there you have 1 nanohenry per square, you make a couple of hundred of microns, and you get your inductance. The other advantages, in terms of scalability, the other advantage is that those chains are super long. So they are super long, therefore they have a self-capacitance, which make that they can have also self-resonances, which can be low in frequency and can mess up a little bit your qubit spectrum or interfere, and you don't want that. And with a superinductance made of a disordered superconductor, this becomes much more compact. And these self-modes can be pushed at much higher frequency. So this was some of the possible applications. Many attempts has been done, and of course, the main question here is dissipation, right? Because you don't want this guy in the circuit to dissipate and spoil the coherence of your qubits.
In a sense, because of the electronic granularity that you might have in this, you will still have this capacitance issue, even if you don't have real junctions, right?
It's not the small capacitance between grain, it's really the big capacitance of the line, microscopic, with the ground plane and the environment or whatever.
Because I mean, technically, I mean, you can say, why would I even need this high inductance? I can just meander my superconductor in a fancy shape, get huge geometric inductance, and be done with it. Well, then you earn parasitic capacitance, and here you don't have it. That's the point. So it's microscopic.
The capacitance on the microscopic scale would be equivalent to the capacitance of a single junction, I would say, if you want. Okay. So that's the point, and the big question is dissipation. And what I heard when I was in the train on Tuesday afternoon, connected to the discussion session already about the plot, dissipation and inductances. So we can follow up after on that if you wish, but I can show you examples, famous examples, successful implementation of disordered superconductors into circuits. You have the granular aluminum that has been beautifully used by Johann Popp in his activity in Karlsruhe. Here is a fluxonium where the inductance is these long lines here, okay, which is give very interesting results, and I know that they are continuing working on this, and it's so the T1 was not fantastic, but it's progressing very interestingly. And here is another example from Alibaba. It's a little bit couple of years ago, and the paper came only last year, and the material is a weird alloy, but it's inductive in the same way. Dissipation is relatively controlled, and we could make also like this fluxonium. Those are examples. And before giving the speech to the floor to the panelists, I want to open also to another potential application. So yes, give you an idea. You see, what they need is this value of inductance, and I said 1 nanorib per square, typically for a thin films. So you see that the length is very compact, actually. It's very easy to reach this kind of values. There is something new, which, well, I was discussing that on Monday mornings, that these disordered superconductors, they also withstand very large perpendicular magnetic field. That was my talk about the vortex physics. It was not about application, it was about nonce matter physics. And here what I showed is a resonator that can survive up to 10 Tesla. And obviously, if you if magnetic field vortices, blah, 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 you kill superfluid density, which means that the inductance shoot up. And the inductance can go very high, up to 100 nanorib per square. And if you calculate the corresponding impedance, it goes also very high. And there you can also think of applying disordered superconductors for the circuit QED platform under magnetic field. And couple any of these resonators via the strong coupling that you will get to, for instance, a spin qubit system, which will have a spin orbit coupling that can tune the electric field. You can also envision to couple quantum Hall systems that are very popular nowadays with the graphene platform and the ions and non-abelian ions that are investigated in places in Harvard and at the Vice. So these all are also other kind of application. So now the discussion for panelists. So there is this qubit application, but I think there the main question is what has been discussed on Tuesday: dissipation. Can we keep a superinductance and high coherence? This is a fundamental question that is ongoing and very interesting. An application that I did not discuss here because it's also a big field is traveling parametric wave amplifier, traveling wave parametric amplifier, which are used for qubit readout. Again, they use macroscopic Wilson junction chain, and obviously it's not super interesting to replace that just by disordered superconductors, and this is going on. There are papers already showing amplifiers working with various materials. You have the astrophysical detectors, and what I mentioned before, but it's perhaps just not winning, how to make quantum sensing with new resonators in standard. So I don't know how you guys want to start. The list 1, 2, 3, 4. Perhaps you can start on qubits and discuss your.
I mean, you already mentioned that essentially the question for qubit is, if you can use it for certain application like taxonomy or detected qubit. Even there, my understanding is that you need even more inductance in most cases. So the preliminary experiments that have been done, they were not really protected because the inductance was still not large enough. So that's one direction to look at. I think there were actually people were also trying to mix, both the geometric and the kinetic inductance, trying to make, but then you have to be careful indeed with these modes that you can get so. But the main problem indeed is this question about the discretion and the coherence, which is not necessarily, of course, the same. Because, for example, in these granular aluminum cases, especially in the taxonomy, what has been seen is that it's what looks like a certain number, of relatively strongly coupled two-level system that couple to the cube. Which brings me back actually to what you were discussing, which I didn't really understand well in the picture, but but that's, for example, one question, right? I mean, is this because the problem, of course, of two-level system, right, in a sense, is that there are all these kind of phenomenology which is vaguely understood, but at the phenomenological level. Did you say, okay, there's a certain distribution in frequency and in coupling and so on, and because this, people usually think this is something to do with oxides on the surfaces or imperfection or this residue fabrication or whatever it is, but we heard, this morning, maybe it's also intrinsic, right? And it might depend on the material or the fabrication and so on. But for qubit, this indeed is really important because you can have long T1, for example, with two-level systems, but your T2 is very bad, and then you still cannot use it as a qubit. You may use it as a memory, maybe, but not as a real qubit.
The two-level systems necessarily cause decoherence.
Well, you can try to play around that. Because if your two-level system is also a good qubit, you can play with that. You can start playing games, right? But the problem is that, again, the standard picture is that you have, let's say, a few two-level system which are nearly resonant with the qubit, and they couple strongly to the qubit. But then they also couple to the other two-level system that act as a path. So the idea is that, if you exchange energy from your qubit to two-level system, then the two-level system will relax, and then you lose completely your information, right? Of course, for example, if you just have a few long-lived two-level system which are decoupled from the rest, then you could do this kind of manipulation. Although then it gets a bit more complicated, but in principle you can do that. So they're not necessarily bad per se in that sense. But then you need to be sure, that these things are even better qubit than the qubit you're building.
But then there's this. I mean, even people who use aluminum know that there is some two-level system in the qubit. So if there's not too many, you can just kind of tune away them in terms of frequency and be okay about it. And that's what I know Google just doing. So for every qubit, they do spectroscopy and randomly detune them.
But that's a huge headache, right?
Yeah,
that's a huge overhead because
absolutely.
and also, every time you warm up and cool down and so on, these things shift a little bit, and you have to recalibrate. And if you're unlucky that there's a two-level system in the place where you don't need even for gates, right? I mean, maybe your qubit is good as a good T1 and T2 by itself, but if you use, something that's tunable to your gates, so with whether it's a coupler or the qubit, and randomly by chance, when you go to the point where your gate is fast, but you have a two-level system in resonance, then your gate fidelity goes down. So it's so having this uncontrolled two-level system is not a good deal.
Yeah, I mean,
okay, but that is GLS issues on quantum processors. If we want to stick to the topic, is how to use disordered superconductors. Perhaps we should.
No, but I mean, just to again, for example, I'm very interested to understand better what Anton was discussing, because this is a different, microscopic source, right?
Yeah,
Because
but
the problem,
Anton is in the limit of
strong disorder. Yeah.
a strong disorder, right?
Yeah, which means large inductance, which is what we would like for application, right? But the question is, if you want, the question for me is, if it's extrinsic, let's say it comes from surface in an oxide, right? That's, for example, why people are using tantalum to make capacitors and rather than just use aluminum, because they say, oh, these oxides are less lossy or there are less TLSs and whatever, so use tantalum to make the capacitor, it works better. But that is kind of, material or fabrication issue, right? I mean, maybe you need to polish or cap your surfaces or something. So that's one thing. But if it's intrinsic, you go to this other system and inevitably you get this, then there's no way around. I'd say, I don't know. Or maybe there is a way around.
There is one that I see. I would like to bring that up. It else actually connects to what Benjamin is saying, that there's active research on what determines dissipation for what material. But there's one catch, is that all those applications operate within a single frequency range, like several gigahertz. Just because electronics is like that, it's commercial, no way around this really. However, at least within my humble small contribution to the theory, what is also clear is that you should just go down in frequency and you don't lose in kinetic inductance at all. But then your dissipation factor might if you decrease frequency by a factor of 2, you can gain a factor of 10 in quality factor, at least again in theory. And I saw some of Thibaut's preliminary data on that. I've seen this kind of, again, preliminary. That's what, like, it's not anywhere near there. So I would say this is why we call for a test of this prediction. But in theory, one opportunity that is not discussed and is actually where this nature of those TLSs or whatnot becomes important is frequency tuning. Because again, I don't see why you cannot go from, let's say, 1 gigahertz to 20 megahertz or something, other than because of technical limitations of the devices that are used in control, in signal processing.
The quantum limit.
Yes,
I'm not sure is a limit.
You need readout bandwidth.
Yes, of course, yes. There is technical limitation. I'm not saying that what a stupid world. I see that there's a challenge, but maybe it's worth it because technically there's an expectation that at lower frequency lies much better world. That's the idea.
May I give a little bit of optimism? I think that Anton's limit is really concerning proximity to SIT with superconductors, with pseudogap, all these very dirty things. And between aluminum and that, there is a wide range of materials where inductance can be nanoary or below and can be enough for application. There is still problem of dissipation and particles and anything.
Yeah, but
we discuss. But so the case of Anton is really an extreme case. I think. So that's I'm not sure it fits the.
It is absolutely true, but then the argument stands. Okay, the dissipation mechanism in those superconductors that are moderately disordered, like not close to SAT, is different. Probably just good old quasi-particles. But then there's been a whole discussion of how this life actually unfolds, and the issue is far from settled. And my statement is that if you look into the theory of how this comes about, you immediately realize that there too lies a strong frequency dependence, which is not explored whatsoever, because everybody raised with interesting.
I can tell that at least my observationally, I think over the years that the average frequency of qubit went down. Slightly, not much, but initially people were working more like 6-7 gigahertz. Now it's more like 4 or 5.
And quality factor incidents. I don't know.
I'm just observing a fact,
Yes.
right?
So also in a kit world, conventional TOS noise in kits, it's better if you go to lower frequencies. And we also see that kits at lower frequencies, they have better noise performance. But that's conventional TOS. And I think actually if we're not in that limit of this TOS in disordered superconductors, so the disorder is not that much that we're still there, then I think disorder can actually help getting rid of some of these TOS, because now the fields or the inductance is really from the superfluid instead of having fields everywhere. So in principle, I'd say I've not seen any experimental evidence for this, but I would think if you go to lower frequencies by getting more kinetic inductance from the superfluid, you don't go to DOS stuff, or less at least.
Yeah, so what I could add to this story, so there was this plot the other day which was discussed, this quality factor as a function of sigma 2, so 1 over the inductance, right? So if you go on that, this limit, you have very small inductance, 0 inductance, large superfluid density, and here is high disorder. And indeed, indium oxide are those red points, which are, this is the most disordered superconductor we know, right? With perhaps LSCO. So this is an extreme case. That's why I was emphasizing this point. But you have a series of materials like granular aluminum, whatever. You see, you have lots of people here living in this area where you can, people are able to reach 10 to the 5, 10 to the 6. And 10 to the 5 in quality factor doesn't give you the state-of-the-art qubits, because the state-of-the-art qubits are in the 10 to the 6, 10 to the 7. But there is something to take into account, is always the same story, is that you have a circuit here, right? If you want to implement an inductance, for instance, and you have a participation ratio between the currents. If you work at high frequency, your current doesn't like to go in an inductance. So you have less current in the inductance also. So the participation ratio of the dissipation from this guy is reduced because of the inductance. And the overall budget loss of such a circuit might be still worse, considering, and perhaps can be used. And actually, Josephson junction chains, of course, if we listen to Michel Deboré, he will say they are fantastic in fluxonium. But if you measure them isolated, they are as bad as disordered superconductors. Still, fluxonium are pretty good qubits as far as I understood.
But when we talk about disorder, are there disorders? Is one worse than another? So I get that you say, okay, let's concentrate on the disorder within the disorder superconductor strip, and then maybe we can sort of find ways to keep the other disorder at bay or far enough from where the field is in the circuit, but within the material is, I guess, magnetic disorder is worse than non-magnetic disorder, but
so
I don't know.
Want
for qubits, what's the most harmful, or what's the most?
You don't want magnetic disorder, you don't want quasi-particles for sure. You want a nice capsule S-wave superconductor. But then it's also a little bit of condensed matter. Each materials may have its own physics aspect, and this is where you are happy to have a sort of survey on all material properties and see the ones who are better than others. Beta tantalum is good, granular aluminum is good. This weird stuff made by Alibaba here was good too. And you have lots of people here in low quality factor. Indium oxide is not fantastic for that perspective.
For 3D cavities, I know that roughness is an issue, for instance.
Okay, so 3D cavity are done with clean.
They are
so it's not
yeah.
disorder. It's another topic.
But yeah, so but there's completely different issues. So,
yes.
So along this line, they are all grouped together indeed, but the intrinsic microscopic physics is very different.
Yeah, so that would be, I don't want to discuss particularly that part. I can, but this is not really, this was the topic of Tuesday afternoon. This is just an indication that you have also conductive loss in this material, in the cavities. So,
actually, I have also a question, about point 2, right? I mean, because
yes.
I'm not an expert as much. I mean, I worked a bit on the sonators, but not then on the amplifier side. I mean,
yeah, I did have 1 or 2 slides here.
So maybe you
want to actually see how that sort of works.
Perfect.
It's two random, not random, but sort of thoughts about the previous thing, like about the low frequencies. I think in the kinetic inductance detector world, people are also starting to use like hundreds of megahertz sort of frequencies, actually for practical reasons, because the electronics is cheaper and less power hungry. but it actually means that there will be data, or at least the measurement facilities are there actually to study what you were saying.
Exactly.
Only you need to look up the right.
I'm surprised it didn't happen earlier.
Yeah, but the problem that I have typically in our sort of community is that people don't want to explore all the parameter spaces that we want to actually study here in a way. They want to have their engineering solutions, so you have to do a collaboration where you actually get them interested in exploring there are groups doing combining both of these things.
There will be also the technology. 10 years ago, there was no low temperature amplifier going from 20 megahertz to a few gigahertz.
No, that's right.
It's recent, we can buy now, it's on the shelf, and we can do this kind of study.
The other thing is that there is also this issue of, but it's not very well clearly documented, of unexplained inductor noise. So people who work with like superconductors with, but it's only moderately disordered in the sense of like 100 picoari or that sort of range. They see sometimes excess noise which looks a bit like two-level system-like of behavior, but they can attribute it to the inductor by like separating circuits with mostly capacitance in the same sort of fabrication round. But I don't think anybody publishes this because the framework to interpret this is very, well, it doesn't exist essentially. But it reminded me what you said about fluctuators probably in your inductor effectively could, but it could also be conventional TLS in the inductor actually. So it's not 100% clear that it must be, has to do with the superconductor itself, but it could be.
Yeah, because you see recently there's been these developments of that you can actually organize a TLS out of a trapped quasi-particle. I mean, it's not a well-researched topic, but it exists in the sense that, I mean, once you dig deep into the question of what can come from the material, you quickly realize that there's a lot that can contribute to this life.
Yeah, so I mentioned already that you have these, so you have sort of two kinds of amplifiers that you could imagine. One is if it's purely resonant, like if you would have a resonator that you can create a strong non-linearity and realize amplification like that, but that's typically very narrow band by its definition, obviously. So people have been working first on this Josephson chain parametric amplifiers, where you have a whole bunch of Josephson junctions to create enough non-linearity to get amplification. But then for two reasons, actually people started looking into the more traveling wave type of picture. One is because the bandwidth of the Josephson ones is still typically limited. And the other one is that how much power you can amplify with those is very limited. So if you have like, say 1,000 qubits with one photon or so typical readout power, you will be fine. But like the kinetic inductance detectors typically need like 10,000 or 100,000 photons per resonator. And if you multiply that with 1,000 resonators, the dynamic range of any Josephson amplifier is by no means good enough. So that's actually two reasons why they started doing this. And the first paper here is by Peter Day and Yom et al. So you see here that this is a device that is really, I think it's centimeters long actually in total, with actually a niobium titanium nitride wire that is completely rolled up to fit in a chip at some point. And here they explore with actually a DC current how much nonlinearity they get, or how much phase shift as a function of current here, which then relies mostly on this I-squared nonlinearity that you will have in any system at some point. And there are sort of two versions that you can make there. So one is actually if you put a DC current here to actually create most of your nonlinearity and then put the signal that you want to amplify on top of that. It's called three-wave mixing for reasons that you won't need to go into, but then you create mostly your nonlinearity with a DC current, or you do it with a strong RF pump, let's say a microwave pump, from which you actually draw the power to amplify the signal that you want to amplify. And then you see here that this is an example that it's a random example that I took from literature, that this can be a very wide band amplifier. So it's more than it's typically you can amplify it over an octave of bandwidth, which is the factor of 2, which you can shift around by choosing different parameters or a different pump tone. So these are typically, because they are traveling waves, they don't resonate or something. So you can actually in principle shift your pump tone around and then get amplification in a different band. One of the funny things is actually that if you want to get to higher nonlinearity, which they actually tried to do recently, is that you want to make this wire here narrower and narrower. And obviously then you get a larger impedance, which is actually what you want. But it's also annoying because you actually want to amplify at the end of the day a signal that comes from a 50 ohm line. So that's why typically the things these days look like this. you can do it in various ways, but this is actually the line on which you send this current and get amplification, and there is this whole structure here to create enough capacitance effectively to balance this out and create a 50 ohm line still. So there are all kinds of variations where people put resonators next to it or something else to actually, or IDC type of capacitors to actually balance out the impedance mismatch in essence. What I thought actually was coming back to this loss plot. I don't know whether maybe I have one more slide. Yeah, so this is what I said already. We do this all because of this very high dynamic range. So people have demonstrated that you can indeed do multiplex 1000 M kits onto one of these parametric amplifiers, and that it doesn't run into saturation yet, which is in a way remarkable because it's a hell of a lot of power that you then use in that resonator. I think.
It doesn't saturate you, so a critical current.
Yeah, that's the point. So I think you must use. I think that's the reason why you use actually in this case the niobium titanium nitride, because it has that high gap energy and relatively moderate disorder, so that you can actually create conditions that this nonlinearity only kicks in for a huge amount of power.
And what is the typical inductance per square that we compare?
This is, I think, well, this is from the top of my head, but it might be between something like 10 and 50 or so picofarad per square. So it's very moderately disordered. But I think that is, well, it has two reasons. One is indeed that you don't want to have it crazy nonlinear, because then you can't handle all that power. And the second thing has to do, I think, with this loss as well, that if you would go to higher inductance, then you get loss, of course, and then this whole system, this thing breaks down. Because that was maybe, so you get here a gain of about 20, well, more than 20 dB actually. But if you would be further down in that loss plot that you just showed, this would obviously fail hopelessly, because you really need to amplify your signal before it gets lost in essence. So in that sense, I was thinking like, well, how could you here still win in terms of going to higher disordered materials? But you probably don't want it actually. You maybe want to do it either with the Josephson chain at low powers or with this sort of material at high powers.
I have a question, but essentially what I understand is that material also influences what this E star actually will be. So how large a nonlinearity you'll get. And as far as I know, another benefit of disordered superconductors is the fact that they just have larger nonlinearity.
That's correct. Yeah.
And I mean, because I'm not familiar with the topic, I don't know whether you can actually benefit from that, or it's fine just having some of it. And then, of course, like strong disorder, it makes no practical sense. But on the other hand,
I think that's the sort of balance that you have in this case. That if you would do it with aluminium, for instance, that wouldn't make much sense, because you need an infinite wire essentially to pick up enough nonlinearity to get any gain, I think. But in this case, it has apparently the right balance between being still practical and that the nonlinearity kicks in at high enough power that you can actually amplify a large signal with it, and at the same time not being yet lossy in the sense of the disordered superconductor loss as we discussed.
The one made to pass like this, varying disorder.
I don't think it's.
You need to be brave also to make this kind of study, right?
No, people have done it with like titanium nitride, but that's very similar to this, obviously.
Yes.
But nothing else, I think.
Because I think it's very scary, because you very quickly get a problem with the 50 ohm match, so you don't want to do that. But the claim that you will use the gain and dissipation, is there data?
People haven't tried this, but that's, I think, indeed more because this technology already existed, and then why would you make it more difficult if it works? But this
quality factor of a chain is not good. It's 10 to the 4, sometimes lower. The one that is using 2 power.
Yeah,
which is similar to this other.
Yeah. No, in that sense, I don't know actually. Probably people have tried and failed. It could very well be, but that's then poorly documented typically. Yeah. So yeah, here in principle, you could still indeed think about replacing the Josephson array with a higher, stronger nonlinear material. This was all of this part, I think. I'm not aware of more work in this direction than actually along the same sort of methodology.
Yeah, but it was actually, I mean, the question more or less that I had, the fact that they does support. So for this kind of application, is it clear then when dissipation will be heard, or essentially still not explored and is not clear?
It's not explored in practice, but you can do the math, like how many wavelengths you propagate. That gives you like what sort of Q factor you would need to have to still have amplification.
What's the range of those factors?
When I with titanium nitride, it is over 1 million. That's definitely not a problem. So there is still some room to spare. If you say that with a 10,000 quality factor you would still be fine, then you couldn't in principle go to much stronger disordered materials for this purpose.
Sort of need to match the nonlinearity, the kind of physical mechanism for the nonlinearity you choose to the dissipation that it will bring you.
Yeah, but like in this case, I think indeed the material choice is mostly from the dynamic range perspective. So an amplifier is sort of the stupid way of thinking about it, that you can never amplify more than the pump tone that drives it. And therefore, if the pump tone that drives it is already lower than the signal you want to amplify, you can forget about it. So that's sort of the dynamic range that you want to achieve.
Anything on amplifiers?
Not more than this.
I have a really stupid question. Why do people in the parity amplifier like planar and they don't do stacking? Because technically with aluminum or planar aluminum, you can do really easily like planar aluminum, oxide, planar aluminum, oxide.
Well, because the oxide is also lossy. So, well, we can argue like how lossy it exactly can be before this becomes a problem, but there are actually microstrip versions of this as well, where they do just 2 layers of nitride with a dielectric sandwich in between. And if the dielectric is of high enough quality, then that's fine. And this actually makes this impedance thing easier because you don't have to do so many crazy structures. But that has been done, but I can't hook up the reference from the top of my head. Yeah, sure.
Okay, so that was for the amplifiers. So you see that there are applications. You want to make a startup, you can go with your preferred deterrent superconductor to be successful. Astrophysical detector, I don't know if Peter, you wanted to add something.
Well, of course, we discussed already a lot on the talk. After the talk, actually, I have 2 other aspects. Or if you can just, sorry. Just to get the thinking a little bit running, it was not that there's anything conclusive, but so apart from on Tuesday, of course, we discussed all the quasi-particle dynamic type of stuff, so I wouldn't do that here again, that we have already discussed in length. But another sort of, I think, interesting property of, again, moderately disordered superconductor in this case, is that what we also want to do is make circuits that are actually operating at a reasonable fraction of the gap energy. So in the case of niobium titanium nitride, the gap energy is roughly 1.1 terahertz, so that's rather large, but we make circuits for out of this from, in this case, 300 to 600 or so gigahertz. So that's actually a sizable fraction of the gap energy. And one of the devices that other people in my group are working on is actually where you very briefly, that you have an antenna here that is actually in niobium titanium nitride, and that's of course then lossless in principle. If you have drop radiation below the gap energy, then you get a traveling wave that travels onto this line, and then you actually detect it by having sort of bandpass filters for the frequencies that you want to detect, and behind each bandpass filter is an MKIT detector. And the MKIT detector is at the moment here not so relevant. It's more about what happens here on this transmission line. So in this case, we expect that this radiation travels in principle from the superconducting perspective lossless, and that we are typically limited by 2-level system type of problems, like we are at microwave frequencies. But remind that this is 100 times higher frequency, so it's a sort of also a bit unexplored range. And what you actually would see as an observation here is that we have, if you do a frequency scan, in this case from 200 to 400 gigahertz, you see all these peaks coming up, and that's each resonator here responding to a different color. So this is just the context of the technology. The interesting part is here, like, what is the loss now on this line here? And the point here is that we are not looking into the losses that, like Florence has shown before, like where the loss is about the same order of magnitude as the loss at above the gap energy. But here we want to actually have this thing travel hundreds of wavelengths before being absorbed. So we want to have it a queue of more than 1,000 or so. Otherwise, we lose the signal before it's even detected. So what you see here as a context is the loss tangent of this stuff. And it's measured actually, in this case, in a Fabry-Perot geometry. So we make a Fabry-Perot resonator where this gigahertz or this hundreds of gigahertz signal can bounce around. And you detect it at the end of that Fabry-Perot resonator again with an MK detector. But you really detect then what the losses at these 300 gigahertz type of frequencies are. And this is actually the data. So the blue lines here, or the blue dots, sorry, are here. Actually, this niobium dininride material. It's actually a microstrip which is based on silicon carbide, which it can be also another material, but it's the dielectric that we use. And what you see here is actually that this is FTS data where they try to measure the absorption at higher wavelengths of this dielectric, and you extrapolate sort of what the dielectric loss would be at these somewhat lower frequencies compared to where the real molecular absorption start to kick in of this dielectric. So all this analysis sort of points to cut a long story short, that this part of what we measure is actually indeed due to these substrate mode absorption, so it's not very interesting. But we see that closer at higher frequencies, we really start to move away from this behavior. And it also is unlikely to be TLS if it is TLS in the conventional picture, because we have, of course, microwave measurements of our TLS loss. And if you extrapolate that with some probably crude, but assumptions that fit in the conventional TLS model, the TLS shouldn't be dominating in this regime. So I think this is also an interesting way to actually measure things like what happened. It could very well be that this is also the disordered superconductor kicking in, where you say, oh yeah, but this shouldn't be happening at this very low level of disorder yet. But remind that you are here measuring losses of 10 times 10 minus 3, not close to the normal or like above the gap energy, but really at very low levels. So, you know, this sort of thought I think we want to explore this further, but it's very difficult to disentangle these type of effects from the superconductor effects because they all kick in the same sort of frequency range. But I think it's an interesting platform to explore further what happens at energies which are a sizable fraction of the gap, let's say. I don't know whether anybody has any brilliant insights in here how we could take this further, but
is that relevant to astrophysics, such this frequency range?
Yeah, it's like it's to detect actually to study a whole sample of galaxies that are redshifted at a certain redshift, and what they then try to do is figure out where the molecular lineage of galaxies is to see what age they are, and it's all populations to study type of research. But okay, that's another another talk in a way. Yeah.
Okay. So qubits and deniers don't recommend.
Well, there are actually people going to higher qubits for qubits. I know. Yeah.
Yeah, it depends on the
Yes. So astrophysical detector is done. So quantum.
There was one. Sorry, we discussed with Steven again that we discussed also about these very high pulses of energy that we obviously also saw in the talk on Tuesday, and also that it's still in that sense a bit an unsettled story as well. Like we have discussed that you have sometimes this seconds of time scales that these excitations stay in the material, like for granular aluminium, where we actually see that it recombines in a very strange but quick manner within 10 microseconds or so, or maybe 100 at most. So for our type of case, this is still also a very interesting problem. But I think also for qubits, where, as we already heard somewhere this week, like there is no qubit that is protected from quasi-particle excitations. So you have to understand also how the dynamics of these things happen in the materials that surround this qubit. And I think there is no way to make, for example, these hybrid semiconductor superconductor devices without also some disorder in the semiconductors at least. So I think there's also still a lot of work needed there.
But the you have an idea what this second scale, because often there are multiple times because in the relaxation of quasi-particles, so this very long scale could be associated to what?
Well, it is attributed in the paper on granular aluminum, also in having very long-lived trapping state. But what these are, I guess, it's anybody's guess, I think. But that's you can have another take on this, but that's
it's that observation, right? I mean, like aluminum might be on the millisecond when you move granular aluminum and it gets orders of magnitude longer.
But also different materials, so you can't say it's the same
But
mechanism.
it's something that at least I've met in different materials. This sort of very fast time, then second time, and then there's always these tens of milliseconds, hundreds of milliseconds. Material related, but sort of, yeah.
Even in clean superconductor, don't believe people they are clean.
no.
So that would be more around or top. So to interface it.
It's kind of different, where people who do circuits or things that comes out from clean room, they are not using it actually grown things. Qubit technology is based on Placis grade aluminum. Someone said Placis 2 is the best. And it's not actual aluminum.
I think
It's
they are
brilliant.
starting
There are
to
lots
do
of-
that, no?
You can fusion things everywhere.
I think, is it that much better with epitaxial aluminum? Because I think people are starting doing that.
So it was the old work of Martinez, who showed that was good indeed, better, but it was one work. So the problem of this is dissipation. It's always a small study in a very restricted parametric space, with always lots of circumstantial issues that makes that studies are never reproducible from nobody reproduces. It's like COVID science, and so there was one work by Martinez and Chris Palstrom a long time ago at UCSB, and they made pretty clean. In their data, it's clear that the epitaxial one was better. It's not a factor 100. I agree.
Because there are studies.
There was a small improvement now.
I know. I mean, I'm a bit more familiar with qubit, and this exploration of material is it takes time and effort, right? And so I agree that it's not really done systematically, and but probably should be done at some point, right? But again, it's like the problem is that, for example, right? If you think, who that the resources are the companies, right? They would have a lot of manpower and money, but they're not interested in doing that because for them it's not commercially interesting, right? And if you are in a small academic lab, right, you don't want to spend 5 years to publish one paper on exploring 3 different materials, right? So it's not clear who's going to do it. There are no right incentives to do it.
Well, there are groups that are doing that.
So you have
Armstrong in I think Santa Barbara or something is doing all this. Armstrong.
Yeah, Chris Palstrom. He was involved with Martinez.
Okay, but
15
he's
years
still
ago.
working on that.
Yeah, I know.
It's also it has to be also try to clarify where indeed your main source of dissipation comes from. Because one example is niobium-based qubit. Okay, so Ustinov tried to make some niobium-based qubit, which means that in practice you do niobium, you deposit some aluminum, let it oxidize to make the barrier, and then you do the other niobium deposition, right? So he got, like nanosecond lifetimes.
Yeah, but
this
is what I call circumstantial problem.
Yeah, this was about, and this was, I think, maybe even 20 years ago, so a long time ago. But even then, those were bad qubits. I mean, there were qubits already which were 10 or 100 times better, right? And then then everybody stayed with aluminum, aluminum. Then David Schuster, a couple of years ago, he made a little change. After oxidizing the aluminum, he added again some aluminum before depositing the niobium. Now the junction are much better. So, but you see, he tried and he got something. But so
good example, IBM has among the best fab and performances in quantum processor. Their average T1 on a chip not the isolated qubit on a chip. You can get make data mining and get all the quantum processor on the planet and get everything. T1 is about 400 microsecond-ish or something, which is amazing. And on the chip with all the resonators and coupling. Niobium technology. The famous super complicated niobium, they made it.
But I think Google is still aluminum based, and they got maybe not 400, but maybe 100, 200.
So you can get 400 with niobium, aluminum, tantalum, but not indium oxide.
On the other hand, this actually makes me wonder whether there's some situations where you can actually exploit this lossiness, because there's this dissipative qubit, care qubit or dissipative care qubit business, which is happening in Alice and Bob. It's like complete departure from the transmon business. And it seems like, well, I don't remember exactly the outline for this particular sort of qubit, but at least there they intentionally provoke dissipation to lose photons, which seems like a very good place for something that is lossy, but otherwise compact in the sense that you can get kinetic inductance as you like. And I don't know whether you followed any developments in this direction, because it feels like you can combat dissipation endlessly. Okay, fine, don't use these order superconductors. Then you're stuck with your TLSs, still quasi-particles. Still, you can spend like decades improving this performance percent by percent, reaching this infamous quantum error correction threshold. But maybe you should just switch architecture. And I'm not saying that. I mean, nobody has thought about it, but then there's again this resource problem. So I'm wondering whether there's anything happening besides this one. Maybe Amazon also.
Amazon has also a similar approach.
Yeah, because it seems that this is where you can actually, to some extent, at least benefit from dissipation, and then maybe you just like that you remove one major drawback of your system. What's your take on that?
I mean, the main reason there is mostly that you give more weight to a certain type of error compared to the other. Then you make it, like this threshold are higher. The error correction comes in. Yes. Because instead of doing like surface code, you can do repetition code with maybe a little bit of. So instead of having a large square, you can live with a ladder essentially, more or less. So that's the advantage in sense of overhead, hardware overhead for sure. In terms of I'm not really an expert. Maybe you can say something more. Does it hurt you more? I mean, if it's different channel of dissipation, because you look at the quasi-particle in the cut qubits, right? But is it worse if it's losses by TLSs or something? Do you have any idea?
Well, I guess if your losses are into TLSs, I mean, it's a driven system, right? So their losses are like constant. So the question is, what happens to this end? So in their current architecture, they evacuate it. It just goes to the external world quickly. But if you have your disordered superconductor, you start pumping it, and you have these TLSs, you have this dissipation. Where does the energy go?
You get some kind of overheating, you mean?
Yes, I guess you don't evacuate it.
Yeah, I mean, of course, then becomes an issue with cool down. That's probably the issue, but so that you have to thermalize your.
No, but we already know. I mean, like you have all this retapping effect and so on. You use regular particles. So, but it's not clear. I mean, whether it's right essentially. For example, even just thinking about regular quasi-particles, right? Because when they recombine, okay, you got rid of them, but if that phonon hangs around too long, it will break again per pair, and then your quasi-particle will not be gone. So that's one example in which, how you get rid of this energy might be important.
Before you were talking about protected qubits. What do you mean by that?
Yeah, no, there was a slide. So it's some circuit scheme in which if you reach certain regime of inductance.
It's a sort of a second harmonic versus first harmonic thing, or?
Yeah, well, yes and no. I mean,
Just to find.
Yeah,
To find things, and you need large inductance. It has to be symmetric, blah blah blah. But it has been also discussed recently that there is no free food. Actually, it's never fully protected. There is always a channel of dissipation that kills.
Yeah, it was
That's what I understood. But
Now, what I know is that, in this kind of picture, again, it depends on, because there are, different circuits, but at least in some design, the problem is that the inductance you need to get into this regime is much higher than what people have realized so far. So that's why they call them like partially protected or something, because you see that it's moving in the right direction, but it's not there yet.
yeah, so my take overall is that there are two communities that are one, which is our very small communities of disordered superconductors, and this gigantic qubit community. Go to the March meeting, there is 2, 3 double room morning and afternoon 5-day session on quality factor, qubit and coherence, right? Recently. And people are now more and more shifting a little bit of this aluminum. It started with this tantalum stuff initially, which was a big tick to the community to leave aluminum. And there are applications from amplifiers that is ramping up. I think for the stories of real circuits, coherent circuits, it's not over at all. I mean, as I told you, I visited Karlsruhe and Johann Popper's very promising data with granular aluminum, quite large inductances. And you can also think, we did not discuss about it, but there are plenty of other possible applications. In a quantum processor, there is one element which is never discussed because it's a little bit boring in terms of physics and application. There is always close to a qubit what is called a reset resonator. Because when you play with all your qubits, it's good, but you excite, they are in many states, but at some point you need to reset, to restart your calculation or whatever. And there is what is called a reset resonator that you put in resonance with your qubit and evacuate the energy. And for that, you want dissipation. And if you can make a super compact resonator which has a miserable quality factor, you are super happy. So you see, I think there are plenty of
potential for
expectation.
super crappy resonator.
Or very crappy.
That's not true.
In between, I think even 10 to the 5, which is the case of 6 for low resistance granular aluminum or other materials. I think there is room. It's just that the qubit community has to also play with all these materials, find their way. You need a tool each time. You need to adapt your process. It's a super long process. I think it takes a huge time.
But also, yeah, it's also, you have to understand both for qubit and also for 2-pass, right? I mean, you have different circuit elements, right? You have the inductor, you have the capacitor, you have the junction. So, and each of them might have different type of losses, and you want to optimize them all. So it's not an easy problem, right? So, because, for example, essentially what has been done in qubit, mostly all this tantalum business or niobium and so on, is on the capacitor. So the only thing, the inductors is a bit on this granular aluminum that Johann Popper has been doing, and on the junction, except for this niobium junction by the Schuster, otherwise it's always aluminum side aluminum. So yeah, there's a lot of still potential things to explore.
People are starting van der Waals junctions.
Yeah, okay. Well, it is there are also proposals to have this different kind of like also different also with twisting different angles.
That is very exotic, but MIT made very nice van der Waals with niobium diselenide and boronitride barrier junctions and enhancements, and got relatively decent.
People have tried also with graphene and so on.
I don't know.
Yeah, I think somebody in the Netherlands.
Yeah. Okay, but what I'm talking about is.
I think there's one person in the audience who actually fabricated transmon out of graphene.
Yes, Nicolas.
What's working school?
It was SNS junction, right? So I'm talking about a SIS junction, and they got T1 of the order of 15 microseconds. She's dealing with weird flakes, was already pretty positive barrier for the tunnel barrier.
If I can make a comment, Benjamin, though, I've read in some of the papers that people claim that, of course, these niobium selenides are good for magnetic field resistance, but they forget to name one important point. They're good against in-plane magnetic field. There's nothing you can do against out-of-plane magnetic field. They're even worse because it's very easy the vortex barrier entry to niobium selenide is very low. So your dissipation, the Livingston barrier is very easily overcome. So everybody who tells you, oh, these are great for magnetic field resistance, they should put a little star with the conditions apply only in plane field. Okay. As long as your field is in plane, this is great. You can run. I built Josephson junctions that operate up to 8 Tesla. Yeah. So,
So that's the different real the magnetic field aspect. Yes. So the MIT data I was discussing was zero field standard.
Yes.
Yeah, so this is a good point. But in principle, you can make the whole qubit, right, from the last materials. You can make the junction. You can make a parallel plate capacitor that has also been done, which is in principle dangling bolt free. TLS should be very, very good in principle. And the large inductance you can also make from single layer niobium diselenide, which recently been measured to be, well, about 1 nanohenry per square. So yeah, you can make a whole von Orell's qubit if you.
Yeah, so there was so at MIT they worked a little bit on that, and what they showed is that if you make a bilayer BN barrier, there is a magical configuration, gift of God, like the aluminum oxide barrier, which is that if you target the resistance, the tunneling resistance of a transmon, which is 5 kilo-ish, this corresponds to about 1 micron square of planar surface for your junction. It's a planar junction. And if you calculate the planar capacitor of 2-layer BN, which is 0.6 nanometer thick, you get 100 or something femtofarad, which is also the capacitance expected for transmon. So in the same device, you have a square, which is 1 micron, so ridiculously small, so you cannot couple to everything, but it's a induced junction where the self-capacitance is the capacitance of the transmon, and all the electric field is only through a crystalline insulating barrier. That is, I think, so it's not disordered material, it's 2D materials aspect for application. So far, nobody has made this kind of ultra small qubit, which, by the way, cannot be scalable because you cannot couple, they are too small. But you can imagine adding more layers of BN and make bigger surface and perhaps.
Yeah, from semiconductor industry, there is a push to 2D materials to have it grown properly, or at least selective area grown. So, I mean, there is maybe a future where you can make this easier than just stamping flakes.
Is there any kind of take-home message to go back to this disorder superconducting in between using sort of uniform disorder superconductors versus grain, like granular aluminum disorder superconductor?
For application, I think it's just you care only
if it
on
works.
the inductance and on sigma 1 and sigma 2. So you want inductance and you want low dissipation. So GRAL is good.
Because we would expect these grains with all these sort of capacitance coupling and things like that would be maybe more dissipative, but apparently so
I think
factor can be very high.
GRAL has specific physics that you cannot map to another granular materials. You know, aluminum, you increase disorder, TC increase. For instance, this is Yuval Oreg. Yuval would not be happy with that because it's against the Finkelstein theory. So disorder, TC decrease. And we don't understand aluminum, so I'm not sure if another material, granular material, will be as good as aluminum.
So I can only add to this that like one particular issue with granular materials is that there's no satisfying microscopic theory. I mean, you can apply all you want to your phenomenological Josephson junction models, but those are models. No, there's no way you can derive them, and basically, once anybody mentions that it's based on grains and islands concept, it's ridiculously small. It does not host superconductivity. So what kind of superconducting phase are you talking about? I mean, it's fine to understand some phenomenology. For instance, this morning we saw a talk that argue that, well, if you accept the network model, at least at the phenomenological level, it explains something, and it's a good approach. But then once you care about understanding sigma 1, sigma 2, or even being able to reason about temperature dependencies, like you're in the woods. And this is particular problem of granular aluminum. And I mean, in addition to that, like you might have complicated physics from grains, and because maybe it's somewhat spiritually similar to strongly disordered superconductors that I've shown. I mean, you might expect similar physics, but then on top of that, you might also expect good old quasi-particle life, which is also very complicated, as we know. And then good luck figuring that out. And indeed, what you're left is as an experimentalist which has only finite time on the earth, is to just accept, okay, sigma 1, sigma 2, whatever God gives to me, I'm working with that. Because there's very little way that you can disentangle all those dissipative channels and all that. I mean, it's a nightmare. And that's, in this sense, I mean, maybe conventional disordered superconductors are just better because, okay, you just take your sigma model and solve everything.
Then you have all the circumstantial issue. You make your GRAL, I don't know about your GRAL, but if you look at the GRAL in Karlsruhe, it was good. But 1 year ago, I forgot, Yale made 1 order of magnitude better quality factor for the same inductance. What do they have? Better fab, better pool. So this is the tricky part. You ask which material to choose. So we made this overall survey. This gives indication. It doesn't mean that tomorrow there won't be indium oxide resonators at 1 million. I don't know. Not the plus.
Yeah, but see, even if we look just at GRAL, right? I mean,
yeah, GRAL is
the span on this direction is like what 2-3 orders of magnitude, right?
Exactly. So these are part of data that, if I remember, are from KIT, and those lines here are Yale, which outperform by far. But then, is it geometry? Is it substrate treatment? Is it this is the super complicated aspect.
Keep in mind that Michel trained Johan, and I think the guy that was back there might have been a postdoc or a student with Johan that then went back to Yale. So it's the same people in a sense. So it's not like they're probably doing things so differently. So that's why, yeah, I don't know. I mean,
clean rooms.
No, that's what I'm saying. That exactly. Or even the same people using different, like
different tools,
different tools, different machines, right? And you get different results. So it's
yeah. Geometry also changed. Recently, they are more and more into very dilute, extremely dilute configuration. The progress is also, of course, here you have plenty of resonators that were done the whole time where the design and geometry was not optimal. Okay. Is there any questions, topics you would like us to discuss or you would like to discuss? My overall conclusion is that I think we are good to go for applications with these materials. For instance, I know that Michel was very unhappy with this plot because he did not want to see the community high inductance material to be not suitable for application. But I'm not that pessimistic on this plot. For me, it's actually showing that indeed don't touch indium oxide if you want to make your own circuits, but that's fine. But you have still quite inductive material that can be useful. And again, 10 to the 5, 10 to the 6 is not that bad at all. Because all current does not flow in the inductor. And the overall budget of a circuit is a very complicated thing. And, yeah, so I think that's my take. Your conclusion, please.
Yeah, I think you're right for particular applications, but like for us, that is, as we discussed, the other axis of what the quasi-particles do, because we desperately want to measure those for some, detection reason. And there, I think it cuts off at a whole different level of disorder where it's still useful, I think, as far as we can tell now. Of course, like we said already, it's been based on 3 data points like titanium nitride, aluminium, and beta-based tantalum. So it's a bit tricky to extrapolate that very widely, but still.
Yeah, but I think both this question about the lifetime and energy scale for trapping, they're also relevant for qubit if you want to use this more disordered material, because again, either you protect the qubit from the generation of quasi-particles, and then if they don't get generated, then you stay happy, right? But if you cannot protect completely, you probably cannot protect completely, right? And then when they get generated and in this disordered material they live for seconds, then I have a question whether that's also a good outcome. I'm not sure, right? So even if somehow you suppress the generation, but then they live for very long.
If they are trapped and don't go to the junction.
Yeah, but it's not clear again. And then it's related to this question of this energy scale. Are they really trapped? I mean, and then again, you don't worry, or they are weakly trapped, and then even just your qubit can kick them out, and then you won't work. Right? So so I think also from the theory side, this together with the experiments, try to understand where this lifetime comes and this trapping energy scale and so on. It's still both, I think, for experiment and theory.
You want to conclude?
Well, I mean, of course, it seems to me that there's fundamentally a lot of open questions about all this discussion, because I would just like to observe that there's not like a simple framework that you can apply even to for a particular material. So you're given a piece of metal, and you're asked, okay, is it good for this or that? I mean, yes, you can characterize it, but then like, what questions you ask as a theoretician, how to separate materials quantitatively? This discussion is far from over. It's not absolutely a clear-cut obvious. And then this, I think this is what actually is important for applications. So once you think of something, I mean, you have an idea what another device that you'd like to implement, some protected qubit or whatnot, you have to be able to clearly say, okay, I picked this one. And we're nowhere near there. So fundamentally, as the questions from the audience suggest, there's a lot of things to be done about it. So even if you don't think that this particular material, disordered one, serves best for your application, it still probably makes sense to study it like fundamentally, because it paves the way for this general understanding and classifying what can happen in those materials, how to think about them, what are they good for, when they are not good. And I mean, this is the type of statement that I would like to make, and I really would like to engage with those. And yeah, as for applications, I'm the least experienced one, like not least of all because I've never touched an experimental device. So,
but me neither. Don't let me touch an experimental.
Yes, declaration is.
Yeah. No, but I would add to that if, of course, there should be also some kind of feedback loop, right? I mean, in the sense that you measure something, material, okay, it works at this level, but okay, it has this much dissipation, right? If you understand where it comes from, is it the surface? Is it simple? Then you can think, okay, if I do atomic layer deposition instead of evaporation or whatever, or if I clean the surface, if I recap it, right? If you understand the mechanism, you can think maybe of improving the material of the fabrication process. But if you don't understand, you're, like walking in the night, right? I mean, you have no idea where you're going. Yeah, if you try a different fabrication, then there's a large probability that it will get worse instead of better.
I've seen this talk at the conference that Google organized a couple of years ago, when there was a talk that guy said, "Oh, we just applied huge voltage to our aluminum oxide and it got better." Like huge is like volts plus 7. Okay, right. I mean, what did you do? Well, we don't know. What have we done? But it got fine. I mean, this is the situation where we are right now. So.